Awesome, thank you. Great to be here, albeit virtually. Strange not being in Frankfurt this week, but so it goes. So I'm in Kendal, in the Lake District. This is genuinely what it looks like around here. It's lovely. Anyway, so first up, I'm going to throw this up because we can. We're quite enjoying this week here at ARM. So as I'm sure most people are aware by now, supercomputer Fugaku just took the #1 slot on the top 500, and this is built by Fujitsu and uses their own core design called A64FX, and that is an ARM-based core and is the first implementation in the wild of SVE, which is the topic of the talk today. So what I'm going to be covering is where we are, a little bit of what SVE is, why I think it's interesting for HPC. Hopefully that's fairly obvious right now. But I guess more importantly, how important LLVM is for this. And so, I mean, this is one machine, and that's great. Cray HPE are also selling this machine, and Fujitsu, or rather, they're selling a system with these cores in it, and accesse Fujitsu, and all three of the vendor compilers that support SVE and support A64FX. So that's the Cray compiler, the Fujitsu compiler, and my compiler, so ARM compiler for Linux, are based on LLVM. And I think that's an important point. Okay, so yeah, so we're going to start with a very brief introduction to some concepts for those of you who are less aware of kind of the ARM architecture and what SVE is. We're going to spend some time talking about some changes we've needed to make to LLVM IR in order to support SVE. Then some time talking about the features that the SVE instruction set has that are interesting to LLVM, and how we can take advantage of them to improve vectorization and things. And then there's a couple of slides talking about where we are today and where we hope to be over the next kind of year or so. So I'm not going to spend a lot of time here, but the slides will be distributed later, and there are links in here to places to read more about these. So we'll introduce SVE properly in a moment. One other point here is SVE2, which I wanted to highlight. So SVE was designed for HPC workloads, and its reason for existing is to be a good architecture for HPC. SVE2 widens that to a large number of other domains and gives the SVE vectors and instruction sets parity and more with Neon, which is our previous generation of vector architecture. And that's interesting for this audience because that should give an indication of how, number one, how seriously ARM is taking this. This is for kind of all domains in which kind of ARM A-class processors play, and why that's important to LLVM. Like if you look at other places where ARM is used and what compilers they use, then LLVM is a big player there, and the foundation we're putting in for SVE is vital for those markets. So that's all I'm going to say about SVE2 for today. Then the other thing, the other concept you need to know about is called the ARM-C language extensions, or ACLE. Now, I'd recommend anybody with an iPhone to make it face down, because the words ACLE sound an awful lot like Hey Siri, and I really don't want to activate your phones. Okay. So, but yes, what is this? It's not that. It is a set of C intrinsics that allow people to write something very similar to SVE assembly but it's more easily maintained. So it's a set of intrinsic function calls that get mapped by the compiler to individual SVE instructions. Okay, and then there's a couple of more links here to the ARM v8 architecture, which is what all of this builds upon, and the most recent revision of the ARM v8 architecture, which is v8.6. Okay, fine. So just a little bit of focus for those of you who aren't too aware of what SVE is. It stands for Scalable Vector Extension. And the key and interesting bit for us is that that's a scalable word. So it is fundamentally a set of vector registers and predicate registers will come on into, and a set of instructions to use them. But the interesting part of it is that the length of those vectors is not known by the compiler at compile time. So you can make a 128-bit implementation of SVE, and that's fine. Or you can make a 2048-bit huge implementation of SVE, and that's fine too. Or any multiple of 128 in between. Now, as it happens, A64FX is a 512-bit implementation. But that property of not knowing at compile time how big your vectors are is important, and is a big kind of part of the challenge of adding support for this in LLVM. And then the second concept we need to know about is predicate registers. So this is it's a vector architecture extension, and it's also a fully predicated extension. And so we have predicate registers, which it's easiest to think of them as representing individual lanes within your vector. And the width of those lanes, of course, will vary based on your data type. So it could go from 8-bit up to 64 bits. And all but one of the bits in the predicate register will be, for a given lane, will be ignored. So the predicate register represents a binary flag that describes whether this lane is active or not right now. And you can do comparisons to set them and so on. So those are the two new register types we have. Okay, so let's jump into the first of the two sort of technical parts of the talk, which is about how to represent that scalable property in LLVM IR. And oh yeah, hopefully Zoom isn't getting in the way, and in the top right hand corner you can see three circles here. These represent kind of where we are and how well implemented this is in LLVM today. So green stuff is things that work well and is implemented and is fine. Orange things are things that are in progress, and red things are things that are not supported yet. Okay. So we have four things to talk about with the LLVM IR. This is a little bit of a simplification, but these are the most important kind of points here. Okay. So first of all, we need to add the idea of scalable vectors to LLVM. So traditionally, you know how wide your vector is at compile time, and so you can have a type declaration like this, which says you have a 128-bit vector consisting of four 32-bit integer values. Okay, so that's fine. But with SVE, your vector size, as mentioned, is unknown. So LLVM in the community have chosen to make an assumption that whilst unknown, that value is constant at compile time. So you don't know how big it is, but you know that it will stay the same for the unit of compilation you're thinking about at the moment. So, you know, the module. And there are reasons that assumption holds. So there's a calling convention for SVE, which describes things like, you know, caller saved registers and callee saved registers. And that in combination with the architecture means that if you break that assumption, if you have a function that has a syscall that changes your SVE vector width, you've broken the calling convention. And so undefined behavior, you're on your own, fine. So we're allowed to assume that this is an unknown constant value. Okay? So we have extended the type system in the LLVM IR to include a concept we've called vscale, which represents this unknown constant. So a scalable version of the vector we saw before would be declared as vscale times 4 times I32. So this is a vector which is some multiple of 4 32-bit integer values. So for example, on a 128-bit implementation, vscale would equal 1 at runtime, and you would have 4 elements that you could process at once. On a 512-bit implementation of SVE, at runtime, the same code would have a vscale equal to 4, and you would be able to process 16 elements at once. Okay. So having done this, which is fine, you then need to fix up vector type. So vector type has quite a rich API that allows you to query that vector and understand it. And as an example, one of those functions is get num elements, which tells you how many elements are in this vector. And this and similar accesses are used all over the place. So there's a lot of busy work to do there, where we have to, what we've chosen to do upstream is split vector type into fixed vector type, which doesn't support scalable SVE vectors, and scalable vector type, which does. And then you have to go and find, in LLVM9, there were 787 references to get num elements, some of them to do with vectors, some of them not. And you have to go through every one of those and work out what they're doing and fix it up and change the type if necessary and change the code so it works properly. So big shout out to Christopher from Qualcomm, who is heroically going through all of this at the moment. So, and yeah, this is a work in progress, but it's going well. Okay, next up, stack frame layouts. So traditionally, all of your values on your stack have a known size. It's a similar problem to the last one to some extent. The offset from your stack base is therefore known at compile time. But now we need to support splitting and filling of scalable vectors, and you don't know how big each one of those is. You have an instruction that will write out, 1 or 2 of these SVE vectors, but you don't know at compile time what that offset should be to the next position in your stack. So we've added a scalable area to the stack frame for a function, and this only contains scalable values, and so you can write code that performs this calculation here, where you take a pointer, be it a frame pointer or whatever, and add some known offset, and then also add a second offset multiplied by vscale, and that will give you the address of a value on your stack. Okay, and then the last point about the LLVM IR is I want to highlight shuffle vector. So the point of shuffle vector is to permute the elements within a vector, and the way it looks is kind of like this, where you take 2 input vectors and you conceptually stick them together and choose some elements from across those 2 vectors to go into the result. So as it happens, this pattern here of which lanes you want to access represents a zip low. So it takes the low even numbered elements of the 2 vectors and interleaves them. Okay, but the issue here is that this here you can't represent this as a constant, because this the pattern you need here changes based on the size of your vectors, and so you can't construct a constant pattern like this. And it also holds for a number of other uses of shuffle vector, which have been enumerated, and so there's splats and reverse and concats and so on, the list here. You need a way of representing this pattern. So the solution to this isn't fully decided upstream. The current discussion is around using named shuffle patterns to represent, you know, a low zip or so on, or possibly using target-specific IR intrinsics that return a pattern that can be used by shuffle vector, that sort of thing. As it happens, but because so you know, downstream we did this a different way. We added new constants to the IR that can be used to construct these patterns, but that's not what we're looking at doing upstream. Okay. So those are the 4 main points about how to modify the way the IR works in order to understand scalable vectors. Then the other half of the problem is about making use of what SVE can do to allow more vectorization or better code quality and things like that. So this is a list of 6 things that SVE can do. Shall quickly rattle through. You have per lane predication, as I described earlier. It is possible to remove scalar tails. I'll describe that. It's possible to make vectorized loops that have multiple exits or unknown trip counts. You can handle loops that contain complicated data access patterns like gathers and scatters. It has good support for doing reductions in a few ways, and has good support for complex numbers. So I'm gonna run through those as quickly as I can and describe where we've got to with support for those and what work is left. So per lane predication is pretty easy in LLVM today for the vast majority of people, with one caveat. So LLVM has a select instruction, and so you can, if you have code like this where you have some condition within a loop and execution that is predicated on that condition, then one way of implementing that is you conceptually within the LLVM IR, you can always do that piece of work and then filter out the results for the inactive lanes using select. The difficulty here is if instead of being a addition here, if this was a divide, for example, then you run into the possibility of hitting divide by zeros on inactive lanes, which if you have set up your exception handling to raise an exception on divide by zero, then the processor will raise an exception when the scalar implementation never would have done, and obviously that's a problem. Now this isn't a very common use case, and it's not super important, but and it's also possible to get around this using select, but the full solution to this would be to have first-class predication support in LLVM, which is a work in progress in the community. And when that lands, that'll make it much easier to support fully compliant IEEE exception handling. Okay, next up, scalar tail removal. So I've mentioned we have full predication. We can use that with instructions like this one, which is called while low. It's the job of while low is to construct a predicate that represents the work remaining in a vectorized loop. And this example here is, think of x8 as being the induction variable in your C code, and x9 as your terminating condition. It will compare x8 and x9, and then similarly perform a number of other comparisons where incrementing x8 by 1 each time, so that if you're near the end of your work, then you get a predicate that looks like this, where the elements that would have been executed by the scalar code will have a true predicate, and when x8 becomes equal to x9, then the predicate goes false and stays false. And so with that, you can get rid of scalar tails. So you end up with a loop structure that looks like this, where you have setup code and you have your vector loop, and instead of having a check and a scalar tail here, you use the vector body to mop up any remaining iterations. So, so that's great. It removes the scalar tail, which cleans up the code, which is good. It's really good for code density. It's really good for iCache usage. Depending on your implementation, it may have a disadvantage here, which is if you have a very small amount of real code in your loop, and like this one, and if your implementation of SVE, if the while low instruction is, for example, has a higher latency or is not executable quite as quickly as the standard scalar compare, then you have a dependency here between this while low instruction, which sets up this predicate and also sets up the condition bits that are used by branches, and then a branch which consumes those condition bits. And so it may make sense, and we think we will, to have support for both this form and for a form that uses scalar comparisons to control the loop structure within LLVM and has a scalar tail. Though we may implement the scalar tail as a different vector loop, actually, but it's a piece of detail. And then have the cost model decide which is the best form to use. So that's fine. Right, next feature is unknown trip counts. So if you have a loop example like this one, where you have a comparison within the loop that depends on data that you only know in the current iteration, this is traditionally pretty difficult to vectorize, because if you have a vector that contains, a value that terminates the loop and then contains some other lanes, then you need to not perform anything in those other lanes, or rather you need to have, those lanes must not have any effect on your system state. And an example of where that can go wrong is if your array A terminates at the end of a page and you loaded some values past the end of it, then you could get a page fault, and that would never have happened in the scalar code. So there are instructions that support this in SVE that in particular ensure that page faults are never generated for anything apart from the first lane in the vector. But we don't support auto-vectorization of this in LLVM today. So this is a potential future area, which is why this is red. But it's worth noting that it would be easy to implement a function like this, so using the ACLE, which we'll talk about a little bit more later. And handcrafting such a loop structure is significantly simpler than teaching a compiler to do it. So for an SVE capable implementation of libstring, for example, then you may choose to do that using the ACLE. Okay, data accesses. So if you have indirect or complex data accesses like the one shown here, SVE supports this, and in particular SVE supports gather and scatter loads. Gather loads and scatter stores. And also supports structured loads and stores. So if you imagine a structure of pairs of elements, you can load from every second element or every third element. There are instructions that will do that for you. Now, LLVM has good support for gathers and scatters today, which is great. A problem that we're starting to run into here is that the cost modeling of it is too simplistic. So the cost modeling today assumes a cost based on effectively all of the loads in the gather being scalarized and being done independently, which is overly pessimistic. So for at least some microarchitectures, a gather might be significantly cheaper than that. So we need to do some work there. And there's a pass called interleaved access pass, whose job it is to find gathers and scatters with a regular access pattern, like loading every second element, for example, and replace those with a simpler access, like an LD2 instruction in SVE, which loads every second value. This suffers from a similar problem to shuffled vector that I mentioned before, where the index patterns that it's looking for are fairly hard-coded. So this needs to be updated to support the idea of the concept of every second lane, for example, without having to explicitly describe that as a series of constant indices. Okay. Next up, horizontal reductions. I imagine everybody understands how this works. So you have one or more arrays worth of data which are reduced in some way down to a scalar result. Both LLVM and SVE support this very well. There are two mechanisms you can use here depending on your flags. So you can either have a strict IEEE floating point ordering where all operations are done in the same order they would have been done in the Scalar implementation. So SVE supports that, and that's fine. Or if you give a sufficiently generous set of flags, then it's possible to reorder those operations and get significantly faster code. And so what you do is you stay within your lanes, you generate a partial result for this reduction, and then at the end of the loop you collapse that into the single scalar result. So that's much faster within the loop because you're not crossing lanes, and that's typically expensive depending on your hardware. And the final collapse of that into a single scalar value is also more efficient because you can do a tree pairwise implementation rather than having to do it one lane at a time. Okay. So both of these are well supported in LLVM today. Okay, last point on this is complex numbers. So this is an example here of some C code that has some complex numbers which are multiplied together in a loop. Okay, fine. So these are represented in memory as pairs of real and imaginary data, which each of those pairs represents one complex number. And SVE has operations that support a vector's worth of those pairs and doing all of the math you need for complex number multiplication or FMAs and things directly on those without de-interleaving them first. Now, LLVM has pretty good support for this today for most vector architectures by using SLP style vectorization, but that relies on you knowing how wide your vectors are, and it's more difficult to do that pattern matching with scalable vectors. We have done quite a lot of work downstream to enable auto vectorization of loops like this. But it's not in our product yet, and it's certainly not in upstream LLVM yet, so I've given that a read. Okay, one more thing, which isn't a feature, so I've given myself an extra number there, which is what if you want to just throw all of that out the window and not use it? So it is perfectly, there are good reasons sometimes for users to want to tell the compiler that I want you to assume that the vector width is exactly this, and it's okay for the code that you generate to fail to run correctly on any other vector width. There's a couple of reasons you might want to do that. The first is if you're using the ACLE, which has these intrinsics that take C types that represent SVE vectors and do operations on them, and typically, return an SVE vector type result. Those C types are inherently unsized because you don't know how wide they are. That's what we've been discussing. But the problem is, if you want to store those values within a struct or a class or things like this, the standards, the C and C++ standards require you to know the size of your structs and your classes at compile time. And so that's not compliant with C and C++. So this is supported in GNU today. It will be supported in LLVM. I'll come to that in a moment. If you give this flag, then it gives the compiler permission to transparently cast between those SVE ACLE tags and a standard known width GNU C and C++ vectors. And you can then declare your classes and your structs to use the GNU vectors and use them for results and for passing arguments. And the compiler will transparently cast from that to the SVE ACLE type and back again. And so from the user and the code perspective, it just works. This is important for some people, especially there are some performance possibility frameworks like Cocos and Grid and others who have intrinsic-based implementation of basic operations which need this property. So we're going to add it. And then also, if you give this flag, then it's reasonable for LLVM IR to, that's known width vector IR of a correct size to be lowered to SVE registers or SVE vectors. And that makes it significantly simpler to implement what you need for LLVM to be able to support SVE. And we know that at least some of our partners care about this. So they, for example, may have their own also vectorizer, and they know the width of their SVE, and they want to generate standard LLVM vectorized IR using their auto vectorizer, and then code gen it. Then that's mostly for them. Okay. So those are the SVE features in LLVM that I want to sort through. And two more slides. First up, the status of where we are today. So LLVM 9 had assembly support. LLVM 11, which branches in 2 or 3 weeks, will definitely have intrinsic support, which is great. The last patch that enabled the C-level intrinsics landed a couple of days ago now, which is a really big milestone. Sanders' team, so Sanders, the person leading much of this effort, are currently working on stabilization of that and stack unwinding and debug info and extending it to cover the new v8.6 instructions. And meantime, Paul Walker is busy upstreaming support for code generation of known width SVE when you give the -MSV vector bits flag. Then looking forward, LLVM 12, there'll be a focus on making sure the ACLE code quality is as high as it can be. So if you're using it, let us know. And we aim to have kind of end-to-end kind of full SVE vectorization, so that without the -MSV vector bits flag, of at least a few simple loops within LLVM 12, and then we'll build on that in the second half of the coming year through to LLVM 13, where we hope to have full support. Now, these are forward-looking statements, and it's very difficult to get them right. So don't beat me up too much if that doesn't happen. But that's what we'd like to do today. Okay, cool. Then finally, huge thanks to the other people involved in this effort. There's lots of work happening in my team in Manchester, but there's also lots of ARM partners involved here and the wider LLVM community. So particular shouts out to kind of Qualcomm, HP, Cray, Fujitsu, Lenovo, and Huawei. And if you're an LLVM developer, please get involved. Sander hosts a meetup call, a sync-up call every 2 weeks. There's a sign-up sheet there to get an invite. There's meeting notes of past calls, the list of fabricator patches that people are working on, and reviews welcome as always. And there's a list of things that we know about and who's working on them in case you want to get involved. So these slides will be available soon, I believe, and so you can follow those links through. There we go.